Yeah, so it's my great pleasure to introduce our seminar speaker this week, Decker French. Decker and I went to grad school together at Arizona. So yes, the trend continues of me inviting my friends to come give talks. But this one, you know, again, as you saw, many of you had research overlap interests with Decker's work, which I think was really cool. So she got her PhD from Arizona, I think the same year as me in 2017. Yeah, so, and then she went on to be a Hubble Fellow at Carnegie in Pasadena. And then went on to the University of Illinois, where she has been since then. So yeah, so she's an expert in a lot of really cool stuff that intersects and overlaps with a lot of the work done by the folks in this room from AGN, time domain science, post-starburst work. So a lot of really cool applications of her work to people here. So I will shut up and let you take it away. Thanks.
Cool. Well, thanks everyone. So I'm excited to be here. I've had a lot of great talks today. It is cool how some of this intersects in a lot of different interesting ways with what's going on here. So I want to talk about a number of projects that really get at this connection between supermassive black holes and their host galaxies. And I am interested in this. I'm going to make this window go away.
You have to like be able to see it from here. So yeah. Almost got it. Yep. Perfect.
Years of pandemic Zoom experience. So what do we hear about this this interplay between the galaxy and the black holes? I think this is interesting because it's one of these connections that works in both directions. We know that the black hole to grow depends on the accretion of gas and maybe stars from its host galaxy. But that galaxy's evolution is impacted by the accretion energy from that black hole. So both are kind of affecting the other in a set of physics that involves these really, really disparate scales, which I think is quite interesting. And so I want to start with a statement that is by itself maybe not controversial, which is that we expect EGN feedback to do something, to have this prominent role in galaxy evolution. EGN feedback is something that we invoke in a wide range of settings. So what do I mean by this? What I mean is that if we try to go out and simulate the population of galaxies that we see in the universe, this is hard to do at the high mass end without invoking some source of energy that prevents galaxies from forming stars just forever. So if we want galaxies to eventually stop forming stars and turn into the red quiescence that we see, we need to have some way of eventually preventing that from happening. And in simulations, it works really well if we add in something called AGN feedback. So this is an example of this for a case where a galaxy is forming stars, has a starburst, and it's comparing two simulations where in one case, the galaxy kind of continues to form stars happily after that starburst ends. And in this case, what the simulation has added is that some of the energy from the accretion disk of that black hole, as it's growing from some of this gas, some of that energy from the accretion disk is being fed back into the host galaxy. And you can do this thermally, kinetically, there's a bunch of different ways. But the net effect is that now star formation has dropped more precipitously. It's gone towards kind of more the quiescent level. And if we do this in all of our nuclei and our submitted galaxies, we get something that more closely resembles the population that we see. So I'm going to call this kind of with this entire class of things by kind of the name AGN feedback. What I mean by that is negative feedback, that the growth of the black hole has a negative feedback effect on the host galaxy, and it's from the active galactic nucleus, from that actively accreting black hole at the center. So this helps us to kind of end star formation in simulated galaxies. This also might help us explain the correlation that we see between, in this case, the mass of the black hole and the properties of the host galaxy's bulbs. So in this case, what we're looking at is the velocity dispersion of the host galaxy that correlates over a large number of decks with the mass of the black hole in the center. And this is one of those correlations where, like, if I plotted this and it was the other way, you'd be like, that doesn't seem right. It's not the reason that they're correlated, but they're well correlated over a large range of scales. And this tells us perhaps that these two kind of components of the galaxy grow in concert, and say if the black hole starts to grow too quickly, it's kind of having this negative feedback effect where it's prevented from further growth by stopping some of that gas from accreting into the host galaxy. So AGN feedback might play a role in driving one of these fundamental correlations as well. Kind of backing out all the way to thinking about the stellar mass-halo mass relation. This is thinking about kind of the ultimate fate of baryons in the universe as a function of dark matter halo mass. If galaxies were uniformly okay at turning gas into stars, then this might be just a flat line that would be maybe somewhat below kind of omega baryon, right? Maybe not all of the gas will form stars, but we see it has some shape. And on the low mass end, we can blame stellar feedback. You can say if your halo is not low enough, is not high enough in mass, right? Maybe this is hard to retain some of the gas if you blow it out with a supernova or something like that. And on this high mass end, we often blame AGN feedback to say as that halo grows, as your galaxy gets more massive, then we need this other source of energy that scales with the overall mass versus this that maybe tops out with what you can do with supernovae. So we have all of these places where we'd like to invoke something like this that are quite fundamental. I've drawn this almost in like the kind of red yarn aspect to kind of say we have all these kind of disparate places. It has to do something somewhere, right? If we want to do all these grand things, it at least has to do something somewhere, right? And we have some expectations for how this might happen physically. We have this model where you can have two galaxies that, if they have a gas-rich major merger, you can kind of accomplish multiple of these effects that it needs to do in a consistent picture. So for example, if we have the merger between two gas-rich galaxies, we know that this can trigger a starburst. As those galaxies have especially their first passage and their coalescence, then that gas will form conditions great for star formation, and we can fuel a burst of star formation over a short time scale. This is showing from a simulation kind of what that star formation rate does as a function of time, and also what the accretion rate onto the simulated black hole does as a function of time. That's showing that as we get gas funneled to the center of the starburst, it's also funneled to the center, they use some delay for growing the black hole. And AGN feedback fits really nicely into this picture in the sort of intermediate, like just after the starburst, maybe into the post-starburst phase, where if this is where the energy comes in, it can prevent the galaxy from continuing to form stars and nicely take you from your gas-rich star-forming galaxies to your nice red and dead ellipticals, preserving all of our relations along the way. So we have some expectations for how this might happen, and this model makes a number of really useful predictions. In practice, this effect is very difficult to measure. And there's really two kind of prongs to this approach that we can do. And both of them are kind of quite troubling in how difficult this is. So the first thing we can do is to look for galaxies that have luminous AGN in them. Galaxies where there should be a ton of energy coming off the accretion disk, and ask, are those the galaxies that are quenching? Are they being prevented from forming more stars? And there's usually not. This is a plot that I really like that's showing the star formation rate and also the black hole accretion rate as measured for a bunch of AGN as a function of the amount of gas, the cold molecular gas in these galaxies. And the point that this paper is trying to make is that in galaxies that have a lot of gas, you get a lot of star formation. In galaxies that have a lot of gas, you get a lot of gas accreting onto the central black hole. And so this is trying to explain the sort of contradictory effect that we see where when we look for the galaxies that maybe should be the most affected by AGN feedback, they're just happily star forming. The gas doesn't seem like it's affected by this booming blue out. Oh, so this is tricky because this also still makes sense, right? The AGN is growing where there's gas. And so we can also take the opposite tack. We can look for galaxies where we know that they have recently quenched. And I'll talk a little bit about how we select these in a minute. And we can ask, okay, these things that recently quenched, do they have AGN in them? And often the answer is not a lot. I'll show more of this as we go, but most of the rapidly quenched galaxies that we can see don't show evidence for luminous AGN activity very often. We see something that's more indicative of kind of low-level, weaker AGN that might flicker over time. So I want to walk through kind of the second approach to use some kind of newer methods in the time domain to really try to get a handle on what it means if this and this are the case for what AGN feedback might do. And I should say, having already gone through 3 slides here, please interrupt me, raise your hand. Let me know if you have questions. I'm happy to answer questions as we go. I'm used to, especially in this kind of room, it's easy to kind of be interactive. All right, so I've said I've been looking at galaxies that are recently quenched. So I want to be more quantitative about what I mean by that. And so we have evidence that something like half of all quiescent galaxies today have gone through a phase where they rapidly ended their star formation. This probably increases as we go to the higher redshift universe, such that if we look at quiescent galaxies in the higher redshift universe, then most of them must have quenched pretty rapidly. This is maybe both a function of just having less time in the universe to become a massive quiescent galaxy, and also maybe some different physics at work, action or things like this. And so what we can do to identify things that have recently quenched is to basically look at star formation traced on different timescales. So the parameter space that I've often selected this is to use something like the H alpha emission line equivalent width to trace current star formation. So this is tracing the H2 regions around young massive stars, and the H alpha equivalent width is a good proxy for the specific star formation rate of a galaxy in the last like 10 meg years or so. If you want an indicator of star formation on a longer time scale, well, instead of looking at kind of O and B type stars, we can look for the presence of A type stars. So A stars are at that sweet spot in temperature, right, where they have strong polymer absorption. And if you look at, for example, this is the Lick index, but it's effectively related to the equivalent width of H delta in absorption. This traces the presence of A stars, and because their lifetimes are about a gig-year, it's tracing star formation over the past gig-year. So if I plot all of the galaxies, now I'm thinking about low redshift galaxies. This is stuff from Sloan, so redshifts of 0.1 and 0.01 or so. I can see, all right, so here's some star-forming galaxies. They're forming stars now, and they've got a bunch of A stars in them, and some early type galaxies that have low star formation rates, and they've been quiescent for at least a year or so. And you can see that there's actually kind of this physical spur extending over this way, where these are galaxies that have a mismatch. So these galaxies don't have a ton of current star formation. They look quenched, but sometime in the past year, sometime in the past lifetime of an A star, they must have had a burst of star formation to give us this sort of dominant population of A-type stars. And so this is where we can find our recently quenched or post-starburst E plus A, K plus A. There's more names and acronyms type galaxies. And then we can say, all right, these galaxies, they had a starburst. Now they're quiescent. What happened? What's wrong with them? Did the AGN do something? Do we have evidence for why they quenched? And so a lot of the work that I've done in the past has been looking at the gas in these galaxies to ask the question, what's wrong with them, right? Why aren't they forming stars anymore when they just had this burst of star formation? And one of the things that we found is that they seem to have low star formation efficiencies. Many of them have gas, but the gas isn't forming stars at the same rate as a normal star forming or starburst galaxy. So what we've been able to do is to resolve where some of that molecular gas is with ALMA. So I'm showing some work using CO 3-2 from Adams Garcina's paper in 2022, as well as some stuff from CO 3-2 from another recent study. And if we plot them on a Kennecker-Schmidt type diagram, where we look at the density of molecular gas. So I'm labeling this H2, but it's of course traced by CO. And compare that to star formation rate surface density, either using H alpha, or if you worry about obscured star formation, going to the few cases where you have something like neon, that's a more insensitive to dust tracer, you can see that they seem to have low star formation efficiency. Or the amount of gas that they have, especially at the densities that they have, is very concentrated in the center. We have these very small sizes. We see low star formation rate surface densities, and also high turbulent pressures. We have a lot of gas at very kind of high capital sigma surface density, and also very high lowercase sigma velocity dispersion. That seems to indicate a turbulent reservoir molecular gas at the center. Something that we kind of worry about is, if we have all this gas at the center, do we also have a lot of dust obscuration? And this is something that we continue to work on. I'm super excited. Adam Cersina is leading a WST cycle 4 program that will get mirror spectroscopy as well as some near-camp imaging for 5 of these post-starbursts. It'll be super exciting. This builds off some work that Adam and others have done using Spitzer, IRS, as well as Herschel, Spire data. And this is really going to go a long way towards kind of constraining to what extent do we have stuff buried under dust in these galaxies. I'm also working on a sample of data that use Magellan fire near-infrared spectroscopy. That's work and prep being led by grad student Dr. Chapathi at Illinois. And this is an example of one of the super weird spectra that we see for one of these galaxies. I apologize, this is mostly for like people who are staring at near-infrared spectroscopy. There are 2 lines that are close together, right? That means that dust isn't really affecting one more than the other. This is bracket gamma, where bracket gamma should be. And this is a line that's tracing warm or shocked molecular hydrogen, the 2.1210S1 line. This is super strongly detected, right? There is warm or shocked molecular gas in this galaxy, and there's just nothing in bracket gamma. Can, right, extinct bracket gamma with a lot of dust obscuration, but in this case, we should be able to see something really unusual and cool in the mirror spectroscopy. So stay tuned for a lot of that. All right, so in these recently quenched galaxies, we have some evidence for, right, this low star formation efficiencies, this turbulent pressure, that suggests some source of energy is needed to do this, right? And it seems like we need something probably in excess of what you can get from the low current star formation rates. So we can add another piece of yarn and say, maybe AGN feedback does this. Or more accurately, we can say, if this is AGN feedback, here's how much energy and here's when we need it. And we'll come back to that. The other thing that we've seen is that in some cases, when we have results on observations, we see cases where we have low velocity, maybe 100 kilometers per second outflows. This is far from the kind of luminous blowout phase of like unbind all the gas, put it all at 1,000 kilometers per second, nothing like this. These are kind of similar to the local escape velocity. Of course, we have an uncertainty due to inclination. So here's kind of what that looks like in this like faux channel map, where if I step from the red shifted to the blue shifted side of this galaxy, we kind of see some rotation. Most of the gas is in rotation, but on the blue shifted side, there's this kind of asymmetric, both in velocity and in position component that seems like it's outflowing. This isn't a dramatic outflow. This is like 15% of the mass going out at 100 kilometers per second, you know, kind of on the blue shifted side. And we have something like this, right, where you've got some rotation and then some excess. And as you can see that the velocity profile of this is super weird, right? So we have some full velocity outflows. So this is not much mass, but it's something. This is something that might contribute to, say, the turbulence in this. And one possibility is that if we've got turbulence driven by whatever's driving these outflows, maybe that prevents the gas from forming stars. So this isn't an AGN feedback scenario where we're like blowing out all the gas, not getting rid of it, or maybe transferring it to different stages of gas. But we're kind of preventing it from forming stars more than we're getting rid of it. We've got turbulence, efficiency lowered, outflows. And we do see evidence that this does seem like it's depleting the gas over time. So see, when we look at the molecular gas fraction, so something like the molecular gas to stellar mass ratio, that does show a trend with the age since the burst. So this is from a paper that's looking at the redshift 0.1 for starbursts. So this is the post-starburst age. So basically the starburst is happening like back here. And this is basically t equals 0 starting from when the galaxy has formed 90% of its roots to stars. And we see an overall decline. That's something like 100 megayear timescale. And now similar timescales have been seen for a number of other situations. So a bunch of you are also co-authors on this paper, looking at the squiggle data, right? So the redshift 0.7 starburst sample that shows basically a similar timescale, where we see more gas in the younger post-starburst, less gas in the older. That suggests either some kind of depletion or maybe also some selection effects, right? Some of these might return to form another burst of stars. And yeah, this paper has some super interesting possibilities for that.
When you saying age, time since quenching, is that based off like SED fitting or something spectroscopic?
Yeah, from in this case, this is based on fitting the Sloan spectra and also the Sloan and galaxy spectrometry. This Google sample is fitting the spectroscopy.
It's like taking T9 years.
Yeah. And this is basically it's more than just T90 because we're trying to save fit both an old and a young component. And so we're trying to break the degeneracy with the strength of the burst. We're trying to be able to account for the fact that a young but weak burst might look kind of similar to a stronger but older burst, but they will have different, say, bummer lines relative to the metal lines, stuff like that. So we're trying to kind of account for that versus something like T90 might combine. Also, this is these are really like K plus A galaxies. We have a K component, A component. We can see them. At higher redshift, this actually becomes obviously the data becomes harder. But the star formation history becomes a lot more simple. At high redshift, these are just A galaxies, right? They're A stars. There's no more K stars. There's no K, just A. Yeah. Certainly at like redshift of 3. I'm not going to say in a room full of high redshift people that it's simpler. But the star formation history is.
I mean, I heard you say that.
It's gonna be a rough whiskey hour after this. Maybe buy more. All right. And so, if one of our possibilities for what's doing this, right, seems like this decline is too fast to be from star formation, and so it seems like this is tricky to do from removing the gas. Maybe that's a possibility for some of these. If, for example, aging and feedback is acting, we're going to be slowly depleting the molecular gas through outflows, or maybe just dissociating or heating some of the gas into other phases. This is where I think work like what Johannes is doing with the kind of the neutral and ionized gas traces will be super interesting to see if we can track all of these phases.
So I guess for you, you must have good enough data to be sure. So one thing that we're worried about on the right-hand side of this slide, right, is that like some of these are just fake post-starburst. They're not actually post-starburst, but you must have good enough SFRs from all of the, especially like obscured tracers, that none of those probably are fake. You think?
We have Spitzer iris for half of these. And those, yeah, not fake. The other half that don't, some of those could be obscured, but we have like a total infrared luminosity.
Yeah.
And if we like kind of scale that down by how much we think the A stars are heating it hangs together, that definitely relies on thinking that we understand how much the A stars are heating the gas. And that's certainly controversial, and we hope to measure and actually constrain that more data. Yeah.
That's cool. So that's kind of a prediction. If it's being disassociated, you should still see the atomic gas, right? Are there tracers for that?
Yeah, so for example, there's like the neutral gas or sodium D. There's a good tracer for this. And that would predict that, like, if we compare the slopes, I think there should be like a very slight offset, right? Maybe time or something like that.
Right.
And maybe where it is spatially in the galaxy might be more extended. There's something that actually with Sebastian Sanchez is working on this on something like Manga or SAMU or these IFU cases. It's not trivial to fit every spaxel, like what that CD is to get out the sodium D.
That would be hard, I imagine.
But they're doing it, and that's going to make amazing sodium D maps for the atomic gas for the Manga and SAMU.
Hi, Deck.
Yeah, go ahead, we can hear you.
Can you hear me?
Yeah.
I'm sorry I can only join remotely. I'm Wida. I have a stupid question about this plot. Does this plot reflect some evolutionary trend for the post-starburst galaxies? I mean, for example, those galaxies quenched for like 0.1 million year when they evolved to the quench galaxies like with quenching time of 0.3 giga-year.
Yeah, that's a great question, because that's definitely what we're kind of suggesting by putting them on the plot this way. One thing that we did in this paper is to try to divide this out into like a high birth fraction and low birth fraction to see if we got something similar. And the statistics kind of go away once you cut the sample in half. We saw some more evidence if you look at the wise colors. But yeah, it's one possibility is this is an age sequence. Another possibility, I think David Senden gets into in this paper, is that some of these younger galaxies might be in sort of like the intermediate kind of like the introburst phase. especially if you have a merger where you have a burst of passage and then another burst that coalescence, or if you have a hierarchical system. For example, I know for sure that one of these, here, one of these dark blue points, it's clearly merging, but there's like another thing that's 30 kiloparsec away at the same redshift. Maybe it will merge with that and have another burst and kind of maybe lose some gas before it evolves into these. So I think on average, we're looking at an evolutionary sequence, but really for individual galaxies, they might do something different and we're gonna have a more systematic direction, depending how often we're seeing something kind of after burst one, but not truly quenched.
Yeah, thank you.
So we've had a few things to explain that basically we're saying if EGN feedback is doing something, here's what it might be doing to the gas. That's just an odd way to introduce this, right? But I'm really trying to lead up to this makes some predictions for how strong feedback needs to be and when it needs to act to do this. So we can go and test to see, is this the case? Because a lot of the work that we've done in looking for AGN activity in this is weak. It's disappointing. For example, when we look at the emission line ratios, this is a plot from Yujing for some of these initial ELSAs, they are liner-like, where the emission line ratios require hard ionization, but they're not strong lines. They're not like a true Seifert. These kind of look like retired galaxies in that sense, or liners. Rance has done some work on the X-ray, looking at kind of fitting Chandra data, for example, abstract post-starburst galaxies. These were selected not from an ELSA sample, but from a sample for which we don't think we have a lot of bias against AGN, like kind of what we do here. And most of the luminosities were pretty low. There was one kind of higher luminosity. This is a sample of maybe that were best fit with a certain model. And there's one that has kind of the spectral luminosity of like north of 10 to the 43 ergs per second, where like the AGN people start getting interested. They're on 10 to the 44 or more. These are not strong AGN. At higher redshift, Elmora Almani has looked at kind of the relative fraction of AGN in star-forming passive post-starburst galaxies, and they don't see an excess evidence for an excess of actually luminous AGN. Dr. Yuanza, if you want to see something similar for multi-wavelength tracers at lower redshift as well. But the net effect is that we don't see strong evidence that there's an excess of AGN. If AGN feedback was quenching the galaxies in this phase, for example, these green points, these post-starbursts, have an excess of AGN if AGN is having an excess effect, basically. But it seems like that's not how it works. And often the sentence that I'm left with, I usually put in like the introductions of papers, proposals, is that AGN feedback, if it's doing something, it's not simple and not instantaneous. Because both of those things are like, you can't prove me wrong, right? It's not instantaneous and it's not simple, right? So, but what I mean is that it's not acting in a straightforward way, and there might be some weird and inextricable way that we need to resolve. And what this leads me to is kind of both a problem and an opportunity, which is that AGN are variable on all timescales and all wavelengths, and the duty cycles of this variability are much, much faster than the timescales that we have, say, in that plotted timelines. If we're watching galaxies evolve on like 10 megayear timescale resolution at best, probably more like hundreds of megayears a year, the AGN can go from kind of off to on in much faster than time. So this is the point that they're trying to make in this paper by Hickhouse et al. Using AGN variability from a simulation, where if this is the Eddington ratio, right? So this would be, accreting at Eddington, and this is more like what we've got in the Milky Way. This is over a 60 megayear baseline, where you can have these fluctuations where this is a normal galaxy, Milky Way, and this is like a secret one, right? Like a booming AGN. That this and this are very close to one another in what their stellar populations will look like, right? So AGN are varying faster than the stellar population changes. So this makes it tricky to say use the AGN as they're on to understand the effects, but it also gives us a number of observational opportunities to try to trace this variability and then look at this as a timeline. Because ideally, we could measure this for a galaxy. This would be great, right? To put the AGN on luminosity on a timeline, just as what we've done for, say, the star formation histories. And so I want to kind of look at two ways in which we try to use variability to constrain what the agent is doing in space. So the first uses one of my favorite objects in all of astronomy, which has one of my favorite names in all of astronomy, which is Hani's Warwork. Have people seen like this object? Some yes, some no. What this is something that was found by chance in galaxies. So citizen scientists looking at stuff in the Sloan Geo Sky Survey imaging. And this is not the Sloan image, this is a nice airband image taken with wind. But this is sort of what it looked like in the Sloan data, where this like weird shape, which Hani, who was looking at this as a citizen scientist, called the Warwork, which is what I understand is Dutch for thingy, right? Thingy Warwork. And this looks so weird because this is a nebula that's extremely bright in 03507. But the line is so bright that it dominates the broadband image. So this is a three-color broadband image, right? Which I think this is from the narrow line. In the band that has this line, it just looks like a weird single color, right? So if you put the G band is green, it looks like green blob, or blue blob, if you put it as blue, right? And it makes it look very strange. And so followed observations to get like a spectrum of this weird thing showed there's not a lot of continuum observations here. This is a gas cloud that's being ionized by this thing. And one of the weird things about this object is that to get this to be this bright, this is the gas cloud ionized by this has a fairly substantial light travel time, about 10,000 years. And to get something this bright, you need a quasar. This is not a quasar, right? This is still an AGN, but it's not as luminous as it must have been to ionize this. And so this is a really cool example of a fading AGN. It must have been a quasar to ionize this. Now it's not anymore. It's faded over time. And it gives us a history on this sort of interesting, like tens of kiloyear timescales. So this is one of the most extreme, it's the most extreme example of one of these things. You need very luminous AGN. It has to have been a quasar and a ton of extended gas to make this visible in optical broadband imaging. If you kind of look at like the massive function of AGN, and do the math on, should there be a lot of these in distant Sloan? There are more, right? And Keelan had looked at doing a bunch of these dedicated Gaussian Zoo surveys to try to find more of this kind of blue fuzz. But you need a luminous AGN and a lot of gas to do this. But you can do the same idea if you have kind of wide field IFU spectroscopy. No one's going to give me wide field IFU spectroscopy on just like 100 random targets, but they don't have to because we have things like MANGA to do that. So what we did is use the fact that in MANGA, there's about 93 post-Urbis galaxies between a bunch of different selection methods. And we went and tried to make maps like this, as well as looking at the emission line ratios to rule out just things from star formation, clumps of star formation, things like that. We found 6 cases in the post-Urbis galaxies where if this is just the Sloan theory image, this magenta is the field of view of the MANGA IFU that was used. I made these faux 3-color images where in red and blue, it's just continuum. And in green, this is like putting a fake narrow line filter on the 03507 emission line. So these were the 6 cases that showed evidence for these extended emission line regions that I'm going to call EELRs or extended emission line regions, because I don't want to keep saying Warworkias, right? Because these are much weaker, right? These are much more, in along the lines of the literature of these than they are true Warworks, because they're not that luminous. I also looked for the luminous ones there, and that was hard, and there weren't any. But for example, some of this is caused by the field of view that we have. So in this one, which is straight with the paper, there's purple fuzz that you probably can't see on the projector here. This is actually one of the 4 of his that Keelan identified by eye. This thing is, right? But with Muse, or sorry, I wanted to use Muse, with MANGA, we can see that there's this kind of slightly different structure from the extended emission line region in this case.
Does it connect to the port?
Not really, yeah. It's kind of like here, and the other thing is kind of here. And yeah, that gets at, you can sort of see that there's different morphologies. These things, some of them are like cone-like, some of them are more distributed. And one of the things that we need for this, and still an uncertainty, is you need passing activity and you need gas around. So the good thing about the starburst is that they probably have a lot of gas around in the extended area from the merger that they had. The merger probably helps with this, but we have a better sense for where we do see this than where we don't, where there's not enough gas to see this, but maybe there was enough AGN activity, and that remains kind of one of our uncertainties.
Play devil's advocate, can you
Yeah.
pull out, there's not some like very faint dwarf galaxy underneath the O3 emission?
Yeah, and so what we can do is we can look at kind of the continuum to see what's there, but also this is still ionized from AGN and not star formation. So the dwarf galaxies should look like they have the kind of other the emission line ratio.
Yeah.
So we ruled out cases where we, like in some cases, there was like a star forming clump.
Yeah.
And we just ignore that because that's
So that's based on like emission line ratio. This looks like an H2 region. These don't.
exactly, yeah. So what we were able to use this to do is to say, all right, this basically gets us history. And I'll show some work that's being done by my recently former postbac who's now starting grad school at Maryland, doing cloudy prediction modeling to actually try to back out a history here. What we were able to do for kind of initial study for this was to say, as a minimum, right, just using the Balmer lines and kind of our recombination timescales, what's the minimum amount of energy needed to give us this brightness and this brightness? And we were able to use that to say, okay, what's kind of my lower limit on the AGN history to turn this into a duty cycle? And so what we can do is use the time scale on which we know that this is visible and how often we see it, and compare that to the fraction of AGN that are currently on. And there are a small number of post-starbursts that have some AGN, and to say, if we model that as some kind of duty cycle that has some time between peaks, maybe some duration, then it's on about 5% of the time, and given the lifetimes, you get a duty cycle that's 2 by 10 in the 5 years. This is kind of the schematic that I put in the slides. And Omar did a much better version of this paper that shows kind of the outline of the star formation rate, as well as the AGN luminosity with kind of this episodic AGN behavior where, you know, it might do something like this. It's a little more realistic model, but given kind of this, the fraction of time that this is on, and about how long we see things in the post-starburst phase, this is about 15 years of quote unquote on time that the AGN might act on the galaxy. And when we see it, you know, in the intermediate, in the aftermath.
I think I missed that 5% is based on the 6 out of the 90 whatever, or it's based on like specific properties of those 6?
It's based on the fraction of the post-starbursts that were kind of Seifert on a BPT, multiple BPTs, or were wise AGN.
Okay.
So it would be like the ones that are on. It's like on 5% of the time, but then what's the time between when it's on is what we use expanded emission line ratio for. Then we can say, like, how often should this reoccur? And so I want to move into kind of our next, I'm calling this, you know, kind of a time domain analysis, but my time domain supernova friends would not agree. I'm thinking about the time domain here. Here's when I move into like actually doing time domain on human time scales that my supernova friends will not let me for calling this time domain, which is the really cool opportunity that we have with VLA all sky surveys. So I like this plot kind of comparing NVSS, but also in more first and VLAS over time that kind of illustrates the fact that we have this amazing opportunity. We've got first in 1.4 gigahertz giving us this map of the sky and the radio as it was in the 1990s, and now VLAS, which started in 2017, which is doing you know, a similar analysis in multiple epochs at 3 gigahertz. And I was inspired by this work by Christine and Ellen that was looking at AGN that were radio quiet in first and had turned on at VLAS. This is the direction that's easiest to do given the frequency difference between these sources. Something that is the other direction could just be kind of a normal spectral slope. And I thought, this is very cool. This is like AGN, they're turning on in the time domain. we should see if we can find any of these in our pulsar bursts. We had 93 pulsar bursts in manga, a small sample, but with this, we just have to have it in the hemisphere, right? In the first and the last footprints, which is most of our kind of broader parent sample selected from Sloan, so still 0.1 or so in redshift. We have about 5,000 post-star bursts from different samples. And we found a bunch of cases where it was kind of a non-detection in first and a detection in VLAS. And we picked the 4 best cases where, given there was no possible spectral slope, you couldn't make anything like this upwardly thick to explain the difference. They must be changing over time in a frequency by frequency sense. So these are the 4. So this is the super exciting postage stamps from first between like 1993 and 1998 for these post-star bursts. And all of these are really nice detections then in that first epoch of VLAS. So you see 4 detections. And one of our main sources of uncertainty was, all right, we've seen these changing, but how much are they changing? What are these sources actually when we look at their spectra? That's because this is all at 1.4 gigahertz. This is all at 3 gigahertz. So we wanted to get some targeted VLA observations to get quasi-simultaneous observations in multiple bands to say how much did it rise in this versus this, what's the shape, what are subjects. So we're going to be a follow-up program on these 4 sources and what we found. So this is the flux of frequency. We are first on our limits, our VLAS epoch 1 fluxes at 80 hertz. You can see that we've got all of these have risen significantly since those first detections in the 1.4 gigahertz band. That's great selection work. And some will continue to rise. Like both of these continue to rise in gigahertz between 2017 or 2019. First up in the US background, 2023 when we took observations. So these, I think these are more flat. And all 4 of these showed this peak spectra. I was surprised that these were peak spectra. My others were not. They're like, this is what you're selecting for. But this was great because what we can model these as is self-absorption. And we can say basically, how we model this turnover from the optically thick side to this optically thin component to what we do is we can assume the energy equipartition and get an estimate for the radius, region, the magnetic field, and also kind of that minimum. And so if I compare these sources to other radio AGN, these are similar in spectral shapes to things that are like gigahertz peak sources or compact symmetric sources. And what I've shown here is the post-star bursts are these black squares, pretty much a zoo of gigahertz peak radio AGN. Black crosses here are those Nyland samples. There's also a bunch of things, a similar collection with first and VLAS, and also things from the literature of radio AGN. Our sources are much less luminous than these, so this is the monochromatic luminosity at the peak, kind of 30 Earth per second per hertz, and these are, kind of to 6 orders of magnitude more luminous. They have a similar peak frequency, and what we can do is, for many of these, there was this resolved to measure size, and so you can put these on a peak frequency size relation. There's an inverse correlation, and most of them kind of fall on this. For ours, we don't have a size measurement, they're unresolved. So these are kind of our upper limits based on kind of our highest frequency observations. And if we assume energy equipartition, over here, they're way smaller for the same peak frequency. So I saw this and I was like, I did something wrong. I don't know how to do energy equipartition. Maybe I better dig into literature as to like how the equations I got for this differ from all of these. And that took me a while. And I decided, no, I wasn't wrong. And I compared to these. So these were a sample from Paul, where she did a similar thing with energy equipartition, same method. And they look a little bit smaller. And it's because this is the largest linear size, so something that's like a jet or elongated will be larger than its kind of average radius if you approximate the sphere. But even these are much larger than this, measured in the same way. So these are weird. These don't look like the young radio sources that these are meant to be. People usually interpret these peaked radio AGN as young radio sources, or by young, I mean like within the past like 1,000 years, right? And ours are very different. They're much smaller, much less luminous. And they're not quite on the right place on an evolutionary track to turn into these. Things typically like evolve this way. On the models that we expect, where they kind of get larger and the peak frequency kind of decreases where that self-absorption happens. Ours, they're not on the right track to evolve into these. And this was both confusing, but also kind of an opportunity, because at the same time that we wrote this proposal, looked at these things in 2022, looked at them in 2023, and we're like, could they be transients from black holes being accreted? And we said, well, in the optical, when a black hole is accreted, you get this flare. She'll slide on this in a second. Usually the radio lasts for about as long as the optical. So honestly, unless the radio lasts for like 10 years in these sources, they shouldn't be contaminating our sample. They should be real AGN. And well, that was not what happened. And so this is something where I show this. If we compare to these tidal disruption events, this is where we like test the parallel universe, where I did my whole seminar in this instead of the other thing. So I apologize for the brief and weird introduction to these. But these are transients that we've been discovering more and more, especially in the past decade. They're optical transients, and they kind of rise and fall in the optical and the ultraviolet in months as timescales. They have distinct spectral features, and they're about as luminous, and they last like a little bit longer than a typical like type 1A supernovae. This means that if you make friends with a bunch of supernova people, they'll let you join their surveys, and you can find these in supernova surveys pretty efficiently. As we've been learning more and more about what these look like in the optical, what their spectra look like, kind of getting better and better at identifying them and taking them out from the supernovae. There's now about a dozen of these discovered each year, and we are like truly on the cusp of this being something that is weird and strange to something we can do at an industrial scale with LSST. I'm happy to talk more about that after as well. If the radio does this, we should like never see these by chance. The rate for these is about 1 per 1,000 years, per 3,000 years per galaxy in the post starbursts, and that's kind of rare. To find kind of this by chance would be rare. But then last year, there's a group that had been doing a targeted follow-up of these tidal disruption events in the radio with the BLA. And what they found is this. So some of these things are jetted, and there's a jet that's pointing at us. And the radioluminosity is super bright, and it kind of rises and falls over maybe the few years after detection. But think about the data we had for this. There were some that had some detections, but a lot of these are just uninteresting upper limits on the radio. What they found is that if you keep looking at these things that aren't radio bright, if you wait, something like 3 to 5 years, about half of them eventually show radio transients. And so they couldn't possibly last for 10 years. That would be kind of weird. Very well might be the case, right? This is data through 2023. Some of these continue to rise. And when you consider kind of the typical discovery time of many of our TDEs, right? Some of these, right? This was discovered in 2010. There's many from 2009. Many of our TDEs were discovered, started in 2018, 2019 with CTF. There's not that many years between that and what we have. We don't actually have kind of 10-year follow-up of most of our TDEs. And so when we compare the radio properties of our post-starburst sources with the TDEs, so the copper colors are all those AGN sources, and now these cyan and purple ones, magenta, are different TDEs that have been followed up and modeled in the radio. Our post-starburst sources are actually more like some of the TDEs than they are some of the AGN. I'll talk about some of the kind of how we might know the difference between if these post-starburst sources are TDEs or AGN in a minute. But I want to talk with you about why we think we might get just random tidal disruption events in the post-starbursts, which is that we know that TDEs occur at a higher rate in post-starbursts than normal galaxies. Truly, I haven't pivoted into something else. This is the same diagram we're looking at, the current star formation versus the recent star formation kind of traced by H delta. If you plotted supernova on this, it would be like out here, star forming galaxies, plot the 1As, still mostly star-forming galaxies into some early types. But even though this corner over here, this is like 2% of Sloan, we get like half of the TDEs. The rate in this, once we correct for stellar mass, is like 10 to 20 times higher in these post-starburst and kind of quiescent Balmer strong things. This is where kind of our parallel universes diverge. I'm not going to tell you why I think this is the case. This is something that my grad student Margaret Shepard is working on testing a bunch of these predictions. But the idea is that if we are looking at kind of new TDEs in these radio samples, if these sources are, regardless of whether these are young TDEs or kind of young early radiation, we can basically say that the young radiative outflows in these galaxies are so weak and so it seems as little mass accretion that it might as well be as far as like the amount of energy that's injected into the ISM during space. And shock about this study out of order. So I want to kind of bring us back to put together these disparate pieces from what we were tracing with the radio with what we need to account for with our research for the gas, to sort of make an energy inventory. So the energy that we need is if we're going to connect these radio trace outflows with what's happening with the gas, right? We're trying to kind of connect our pieces of like, if the black hole feedback is doing something, can we match the energy that we're getting with the energy we need? Just looking at the kinetic energy of the molecular gas, kind of looking at the mass, looking at the velocity, in about 2 × 10⁵ ergs. Adam in his paper looking at the turbulent pressure estimated that the energy required to kind of replenish that entire turbulent energy is also about 55 ergs. And if we look at the kinetic power and outflows, we can look at the evidence for kind of molecular gas, that this is something like 41 ergs per second. I think it's something similar if we look at say, the ionized gas and a somewhat different example of post-starbursts by Valley Barron, or the ionized gas in this. And if we look at the energy available, so then I can sort of plot these. If this is the total energy I need in kinetic energy and outflows, I can kind of use this time to say how much kind of total energy time do I need in these outflows. And I can write this to energy available in a few different ways. So I can use the scaling between radio luminosity and kinetic power in winds. So this is following one of Chris Smith's papers doing something similar for luminous radio sources, both not and green. If you look at the wind energy from these, something like 10⁻42 to 10⁻43 per second. And if this was sustained at this rate, kind of doing this for about 10 to the 5 years, this would provide us in the ballpark the energy we need for a bit of our inferred wind kind over time. And if we think that we have something like 10 to 5 years in maybe one of these duty cycles or kind of integrated between these, it seems like there's enough to make. So in the last 5 minutes, I want to really talk about some of the work that the rest of my group is doing in this space, mostly to spark possible other discussions and questions in a discussion hour afterwards, which is that we're broadly interested in using these connections with host galaxies and black holes to understand nuclear transients where we're not sure if they are TDEs or AGN. For example, this is some recent work both from my grad student Maggie Jericho looking at changing look AGN. There's been evidence that changing look AGN had maybe Green Valley host galaxies, and we thought if the changing looks have host galaxies similar to TDEs, maybe that means that TDEs are responsible for some of the changing looks. Seems like that's not the case. The host galaxies are very different. And the changing look hosts are very similar to this normal AGN, which kind of points us to more of these small scale accretionist instabilities maybe causing some of the changing looks instead of externally driven events. Talked some today about quasi-periodic eruptions. These are a different class of after transient that do actually so remarkably similar host galaxy properties to the TDEs. And we think that these kind of weird transients or maybe something like an emery, a compact object, interacting with a newly formed accretion disk from a TDE AGN. And I'm broadly sort of interested in this interface between TDE and AGN activity. For example, grad student Nick Earl has recently published a paper on this sort of weird transient 2020 NOV, which is a TDE that has evidence for a pre-existing disk. So this might be a case where we saw a TDE in kind of a relatively quiescent AGN disk. We see these interesting double peaks in the Balmer emission lines. And it looks like the activity from the flare is being reprocessed through disk. And postdoc Sam Marsh-McDowell is working on estimating the rates. This is recently in the archive. The rates at which we get kind of large AGN flares from stochastic variability, looking at, okay, what's the rate at which we see flares over various timescales at various magnitudes, and where are we going to have flares that possibly contaminate our searches for TDEs? The idea being that TDEs are not very common, they're relatively rare, and if we, they're rare AGN flares, even if they don't happen very often, and more often than real TDEs, they'll contaminate our searches, probably bias the black hole mass functions that we can measure. All right, so I will end there. Apologies for the quick run through those last 4 projects. If you want to talk more, I'm happy to talk about this in discussion and Q&A. So I'll end there. All right, thanks everybody.
It occurs to me, so when you were showing the 4 warp candidates in the manga images, these are not AGN that we know of, right? And so they kind of look like AGN NLRs to some extent.
Yeah, so some of these are. So a few of these are like, I think 3 of these are like definitely super. Okay. Some of these are more like these are in sort of are on AGN.
Okay.
Where they might be faded, but they're still on.
Okay.
These are because of what we said, if we're using this aperture and Sloan to measure it, we're getting
NLRs.
Yeah.
So some of the energetics arguments you were doing with the radio stuff, you could probably also apply to the extents and ionization required to keep these NLRs.
Exactly,
up,
yeah.
Right.
Yeah. So, oh man, I'm going to use one of the slides I skipped, which is recent postback who's now starting grad school at University of Maryland, ASTR is using Cloudy to try to actually map out luminosity history for these.
Okay.
Like what energy do you need to kind of be over time?
Mm-hmm.
So instead of saying like, here's a minimum, saying like, here's our range. She's using both an AGN SCD and a TDE SCD to do this to see if that matters as well, because that should have emission line ratios to model them all.
Okay, cool.
So the connection, I'm trying to, what is it about a TDE that produces radio? Is that still just like normal black hole accretion that was like triggered as the star passed, or is it like just produced by something totally different?
It's so for the ones that are not relativistic, where it's like not a jet, it's probably just an outflow that's finally kind of slamming into some of the ISM.
Okay.
Later. And so if it's that like
an accretion driven outflow then of
yeah.
the TDE material.
Yeah, because like the there's a wind that's driven off of the accretion disk as it forms. And in simulations that kind of forms quickly and escapes. And that wind kind of will travel out and obscure some of the light, reprocess it. But also some of that, like at there's a handful of simulations that have now kind of used this multi-group modeling to say like, what is radio doing, what is the optical doing, what is X-ray doing? But it's still very much an open question of how much of this is jets. Some of these, like one of them, I want to show this because it's neat. This one, the 2018 HYZ, it's actually continued to rise and has now crossed this one, which is strange. That might be a jet that was off axis that's possessed into our line of sight. That shouldn't happen for most of them though. This is rising with like T to the 5. It's weird. But some of these rise quickly too. Something an open question. I think it's probably mostly outflows interacting with the ISM. But some of it could be delayed jets that may still be somewhat along our line of sight, or recessive jets.
I guess that's what the observations show, and now we're trying to figure out why.
Yeah. Yeah, you get one weird observation, the simulator is right 10 meters. Phenomenal.
Yeah, so yeah, I don't know what I was gonna, so the radio emissions come from like radial lobes, almost like for an AGN with.
It's much smaller because we can't actually resolve it yet. Like, so far, ours are unresolved. There's one, I can't remember if it's or not, that there was just a claim that they've started to resolve it over time.
All right.
It's not like a lobe, it's like a slightly wider Gaussian.
My next question was, is there an image of this?
No, unfortunately, hopefully soon, right? Like these things are expanding relativistically, and like this one happened in 2011.
So basically, that size is like whatever, 15 light years or something. Yeah. But it's still legit to do that conversion between L radio and L wind because it's still basically this.
That's a good question. We could assume that, but
I mean, you're making an assumption about how much of the radioluminosity is coming from the extended, even if you can't resolve it, part, and how much is coming from presumably what becomes of the corona, because there's gonna be relativistic electrons in the plasma right over the central part of the disk anyway, which is giving off the X-rays. So presumably those same electrons are giving off radio waves. So that's gonna brighten to some extent also, but if you're launching a genuine jet, there's gonna be a balance, there's some amount of the emission that's coming from the corona, some amount that's coming on the jet, and that's obviously frequency dependent too. So it's not straightforward.
Yeah.
But if we start to see them in VLBI, then we can start to determine how much is coming from what you need for the energetics calculations. But I think, what you're saying now is more just like, there's enough energy there in some form to generate this.
yeah, this is really an order of magnitude
Right.
argument of like, we're looking at sort of like weak and flickering. Here's about how weak it have to be. Does this work? Like, is it causal?
I'm gonna suggest,
So, just quickly, you showed some radio sources that had appeared after. Did you have any disappear?
Yeah, so there are some that disappeared. And for those, we're a little bit more uncertain because depending on what piece, it needs there's a lot of room here in the possible SEDs, where if it is not expecting to be last, is it just because it's kind of very steep in that roof end? So I would like to follow some of those up, and especially if they continue to change in VLAS, that'll be interesting. Definitely the next step is like the things that evolved over the 3 epochs of VLAS. I for another epoch to get to this to see if this has done, this. Let me see if the size is changing with time, and actually then back out of velocity and a launching time.
okay, so let's think Decker again.